me. Double check.
But I can't find that.
Obviously. That is.
All right, we can get started. We'll start off with blood and just describing what blood is. Blood is covered on much for Exam 5. And it's described as a colloid suspension of all the formed elements suspended in plasma, the liquid part of blood. So that's what blood is, whole blood. Is formed elements plus plasma. So plasma is fluid. Formed elements are the blood cells. They're like cells, but a lot of the things are not like normal cells when you think of cells. So that's why they're called formed elements, but that'll make more sense later once I tell you how they're formed. Okay, well anyways, we've all had a blood draw at one point or another in your life, probably. So what they do is they just kind of like go to the median cubital vein and you put a little capillary or tube and you do a light centrifugation. What you can do is the formed elements spin to the bottom and you can see the fractions of blood in this figure. So the fractions of blood include well, you can see the plasma on the top. It's the straw-colored, yellow-colored fluid. Looks like urine, right? I mean, what do you think urine is? Urine is your filtered plasma. But then the formed elements, what you can see is kind of like the bottom 45%. Plasma, plasma. Call this fractions of blood. Fractions of blood, components of blood, whatever you want to call it. The plasma is about the top 55%, on average. And then the formed elements, it's like about less than 1% is that little white layer, about a millimeter of buffy cone. it's white. Contains white blood cells, well, and platelets. Those are the leukocytes. Leukocytes, platelets. Platelets are also known as the thrombocytes. Thrombo means thrombus, a blood clot. They help initiate blood clotting. I'll teach that in another lecture. Leuko means white. So if I call these WBCs for white blood cells, that's another alternate name. And it's a very small percentage of whole blood. It means less than 1%. And most of the formed elements, 45% of whole blood, are the erythrocytes, or RBCs. Urethro means red. So erythrocyte, what is cyte? Cell. The erythrocytes are the RBCs. And so this is about 45% of whole blood. If I ever use the term crit, which is short for hematocrit, it refers to the content of blood of the RBCs, the red part. This is the O2 carrying capacity of the blood. RBCs combine the O2. Nothing else in blood transports the RBCs as much as the erythrocytes. Dedicated for O2 transport. Okay, well, I'll get into gas exchange later. Let's kind of like continue on with what blood looks like, its properties. It's slightly basic, 735, 745, that's a pH range. Okay. So there's some properties of blood. Now, the reason why there's a range, venous blood is a little slightly acidic because it has a higher CO2 content. Arterial blood is slightly less basic because it has less CO2 content. Why would CO2 affect pH? See if you remember this from chemistry. Okay, if you take CO2 hydrated, you get carbonic acid. Now that's a weak acid which can partially dissociate a carbonate. So we'll use this equation a lot in this class. Well, from here on out, but particularly in respiratory. Okay, so that's why there's a range. It's about 8% of your body weight. I've kind of given you 5 liters as the average blood volume for an adult. There's a bit of a range. For males, it's a little bit more because on average, males weigh more, so they need more blood. But for pregnant moms, blood volume can double. All right, some more terms. So I told you what whole blood is, the formed elements, which are the cells plus the plasma. Then the plasma itself, which is mostly water with some solutes floating in it. Okay, if you siphon off the plasma and just leave it on the bench top, the clotting factors will self-clot intrinsically. And then if you don't need the clotting factors for your analysis, for whatever reason why you drew the blood, you can just siphon off the serum. Basically, serum is plasma without the clotting factors. Okay. Serum basically allow clotting factors to react with like the charged surface of the glass tube. you get a clot. Okay. So what I'm writing is then the remaining liquid is quote unquote serum. Can you get it? So that's what serum is. You just go clotting factors in it. Here are some functions of blood. All of these topics are taught in other chapters. For example, I teach blood gas exchange primarily in the respiratory chapter. I mentioned about, I talk about pH regulation mostly on lecture exam 7 when I get to the kidney. I kind of mentioned about how there's superficial and deep veins. You're learning about that now, actually. Like when you study the vascular arm, are you studying the superficial veins? There's 3 of them, cephalic, basilic, and what's the third one? Median, cubital. Let's not open that and just leave that little trash can in the door so we don't have to keep opening it. Thanks, guy. And for protection, the white blood cells, I'll talk about how they're formed, but I'll focus on their function in the immunity chapter. So I'm not going to really give you a lot of board notes for this slide. But this is important. One of the main functions of blood that we want you to know now is that their main job is O2 transport. So since we're studying blood vessels, which blood vessels pick up the O2? Right there. That's where you pick up the O2. The pulmonary capillaries, right? Picks up is really a scientific term. At the pulmonary capillaries or lung capillaries, same difference. How does it do it? It's simple diffusion. You keep breathing the fresh air, which is oxygen rich. There's a gradient for the blood to pick it up. Because the RBCs have a molecule called hemoglobin, which I, abbreviate HB. Hemo refers to, the red blood, and globin refers to the protein structure. And you have myoglobin too. Myoglobin is the protein in muscle that will bind the O2. But hemoglobin of the RBCs, it can bind O2. So just go like this. HB, and put an O2 there, right? You call that oxyhemoglobin when it's bound. So you study like chemistry, and you remember studying like the molecular formulas, but they have names, right? Like for example, what's that called? It starts with a B. Bicarbonate. Yes, you guys remember that. All right, so let's move on. You pick it up and you drop it off at the systemic capillaries. We talked about capillary exchange before too. And, well, this has a more detailed view of what the formed elements are and what's in the plasma. So I think we should note some of these things. Well, what I find remarkable is how small a percentage blood is to the entire body weight. It's only 8%. You see that? So we say blood is precious. Why is it precious? There's not a lot of it. It's only 8%. So if you start losing blood, you can't lose that much, and I think I went over that, right? At what point does blood pressure start to drop? In that one slide I showed on shock, starts to drop after you've lost about a liter, about 20%. But then you kind of look at plasma at the top, and you can see how the figure breaks down plasma and the things that are floating in it. Plasma is mostly water. Plasma, 91.5%. Good old H2O. But what are the things floating in it? some of the proteins and other things listed here. Okay, albumins. So we'll put some proteins. The albumins in the plasma, they provide oncotic pressure, the blood colloid osmotic pressure. I called it BCOP before. I don't want to write it out, just that's from before. The blood colloid osmotic pressure, that's the pressure that allows fluid to be retained within the blood compartment for pressure. Globulins, the one we'll talk about in this class are immunoglobulins. The IGs, basically, for example, antibodies. Sometimes I call antibodies ABs. Antibodies are immunoglobulins, and we'll talk a lot about those later. Fibrinogen. Fibrinogen is a clotting factor. In fact, it's clotting factor number 1. That designation means it begins and ends with clotting factor 1, right? I mean, it's soluble in the plasma, and when a clotting reaction occurs, it has to kind of like come out of solution and become insoluble, and it's called fibrin. So fibrin is the insoluble form of clotting factor 1. So I'll put insoluble. Has to come out of solution to form a clot. Insoluble, soluble. When it's insoluble, it forms all of these threads and strands within the break of the vessel. The big spider's web. And then as blood flows through the web, blood cells get caught. And that's the thrombus, that's the clot that helps stop bleeding so the broken blood vessel can repair. So in my little drawing here, the red circles are the blood cells, but the black represents the fibrin threads. All right, so that's clotting factor 1. And there's other things listed here. You just kind of look at it. Basically, later I'll focus on mostly the blood gases. But let's take a look at the different kinds of formed elements. So I already mentioned platelets and RBCs. I didn't mention the different kinds of white blood cells. They listed in order of prevalence. Now, white blood cells proportionally are the smallest proportion of whole blood. I mean, you can just look at the numbers yourself. 10,000 to 5.4 mil. I mean, it's a very small proportion, but this performs the important immune function, which I'll talk about in another lecture next week. Just to list them by category in terms of what histologists see. Histologists categorize these cells based upon the presence of granules or the absence of granules, so they kind of call them agranular, which means without, versus granular, they got them. Can you see these big granules in the cytoplasm, or can you not? And basically, the agranular white blood cells include the lymphocytes and the monocytes. The lymphatic system, hey, those are the cells. of the lymphatic system, the lymphocytes, the white blood cells there, and the monocytes, also agranular. So all the other ones, list them under granular, neutrophil. Eosinophil, basophil. Now, I'll talk about their functions later. I just want to tell you how they're categorized by histologists. Here's a picture of the formed elements: white blood cell, red blood cell, platelet. It's a real photograph. That's how they look, 3,500x. For us, I just want you to go up to maybe 400x if we ever look at them under the microscope. But I first want to talk about how they're formed, so it makes sense why we call them the formed elements. And we can talk about how they're all formed: red blood cells, white blood cells, platelets. The formation of red blood cells, the process is called erythropoiesis. Platelets, thrombopoiesis. Leukopoiesis describes the formation of the white blood cells. We'll start with the formation of the red blood cells, erythropoiesis, shown in this pathway here. Let me get another pen over here, sorry. All right, so this occurs in the bone marrow tissue, red marrow. All formed elements again, when I use that term, conjure in your mind the three things: red blood cell, white blood cell, platelets. All formed elements stem from hemocytoblasts, this one, in the red marrow. In the red marrow. Hemo, think of blood. Cyto, think cell. Blast usually describes an immature cell that can develop into something else. And so the places where you have the red marrow in adults, for example, sternum, flat bones. Sometimes when I open the chest plate, I cut through the sternum, and I can see inside, and there's this like red paste. And that would be the red marrow. But you also have it in cranium. Whenever I remove a skull cap, I always hold it up to the light, and I can see all this splotchiness because of the blood cells that form in there. Also, proximal femur and iliac bone. Remember studying the medullary cavity inside the long bones? So we got some in there. Iliac bone of the hip. Okay, so those are the places we got red marrow in adults. So what's going on in there? Along with erythropoietin, and also you need iron and B12, you can get on a developmental pathway that forms the red blood cell. A few things to notice: from beginning to end, does the cell get bigger or smaller? Smaller, that's one thing. Formation of red blood cells, erythropoiesis, kind of decreasing cell size. what's happening is as you progress through these phases, you're kind of just ejecting organelles as you don't need them. Okay? Because let's remember, this is floating in the blood. I mean, what are the smallest blood vessels you have? The capillaries, right? British people say capillary, we say capillary. They got to squeeze through there, so they got to kind of get smaller. So you get smaller because you eject organelles. The last thing they eject is nuke. Once you eject the nuke, you can't do nothing, so you're done, basically. Okay, well, let's go through this. You need erythropoietin, ETO, to differentiate past this pro-urethroblast stage. That's worth noting. The EPO is super important. Now, I almost never write it out. So if you need to write it out to know what it's called, do it. I always just call it EPO, erythropoietin. Okay. It comes from the kidney, actually. Okay. Erythropoietin is essential for development past this pro-urethroblast stage. And also note, you also need iron and B12. Okay? Well, B12 helps you absorb the iron from your diet. Well, anyways, so you get past that stage, phase 1 in the developmental pathway. Okay, now you're kind of like committed, and phase 1 is ribosome synthesis. Phase 1. Make ribosome. The ribosome is the rRNA. And whenever you see that, think we're getting ready to make proteins, right? And it's going to be hemoglobin, right? The O2 transporting protein. So we're getting ready to make proteins. So we need the ribosomes for the transcription and translation. If you stain bone marrow tissue, or the red marrow tissue, and you want to kind of look and see what kind of cells you have, these cells, this early erythroblast, they present this basophilia, that bluish purplish color you see. That's the stain they take up. That indicates ribosomes. Okay, that's how the histologist tells what kind of cell it is. They present a basophilia. Okay. So as you go progress, and you're actually starting to make and accumulate the hemoglobin, they call that the phase 2. Hemoglobin accumulation. So I simply abbreviate hemoglobin HB, so I'll just call it HB accumulation. When you start to accumulate hemoglobin, the cells, they start to take up a red stain. That's called eosinophilia. So when you stain slides, you put both of these things, there's something called hematoxylin and eosin, it's called an H&E stain. It's like you just dunk them in there, and whatever cells take up one dye or the other, okay, either the purple one or the red one, it'll just take up one or the other. And that's how you identify what cell's what. So the cells that present in eosinophilia are called normoblasts. So let me underline the cell names here. So we got these blue-purple cells called erythroblasts presenting a basophilia. And we have these red cells presenting eosinophilia. This figure, they call them the normoblasts. They're accumulating HB. And once you get enough, you eject nuke. That's what you see happen there at the end of phase 2. Eject nuke at the end. So by then, you're done making hemoglobin. Obviously, you can't make it anymore once you eject the gene. Eject nucleus, because the nucleus has the DNA, of course. And then you call it a reticulocyte. Reticulocyte. Well, that's just the precursor to the mature RBC. And you enter the circulation at this point. Enter blood. Remember you have different capillaries? The ones with the biggest gaps, right? The leakiest, the sinusoidal capillaries. Sinusoidal caps. That's what I'm writing here. Okay, at that point, you're an RBC, a full-on red blood cell. So we made it to the end of the slide there. Well, I'm supposed to put ejection of nuke as phase 3, so let me kind of retool. Let me write it over here. Phase 3. Eject nuke. Enter blood. As reticulocyte and becomes an RBC. An RBC has this puckered appearance. It's not hard and fast when you become a reticulocyte before or after you enter the blood. It doesn't matter. One thing that's indicative of a patient who might have a slow bleed somewhere is if you have a lot of reticulocytes on a drop of blood. Okay, because it means like you're making a lot of blood because you got a lot of reticulocytes. Maybe you're losing blood somewhere. That's one thing, but I usually don't see reticulocytes in a blood smear slide. Well, anyways, this process from beginning to end, I put this figure here. About 3 days. So 20 hours, get to the pro-urethroblast stage, and you get this color change from this bluish, purplish to the reddish. Eject, reticulocyte, erythrocyte, about 3 days later. So again, phase 1, right here, synthesize a lot of RNA, and then it drops. And as you start to accumulate hemoglobin, that's phase 2. Okay. So the erythrocytes, when they enter the bloodstream, their job is to transport O2. Here are some properties of the erythrocytes, the RBCs. They're dedicated to transporting the respiratory gases. Clear this one. Oh, they're about the same. I don't like this for some reason. These cells, when we say dedicated to transporting respiratory gases, O2 is 1. What's the other? CO2. CO2. So HB it combined the O2. Call that the oxygen. It combined CO2 as well. Well, because let's remember, when you pick up the O2 at the lungs, you drop it off at the tissues. But when you drop it off, it's kind of like, well, now you have room to pick something else up from the tissues. CO2 is like a waste product in your body's tissues. You got to get rid of it. So if hemoglobin picks it up at the tissues, how do you get rid of it? How does blood circulate? After you go through the systemic capillaries, where do you go? Don't you go back to the right heart? And from the right heart, don't you go to the lungs? And from the lungs, you just breathe it off. So think of it that way. A waste product in your body, you breathe it off. So you pick it up at the tissues and you breathe it off at your lungs. The word for this is carbaminohemoglobin. All right, so that's, it transports the respiratory gases. Let's get all the rest of the points up here. It's biconcave shape, and that shape allows it to have 30% more surface area compared to a round spherical cell. And also so the benefit of that is all the cytoplasm is a short distance to the surface for easy gas exchange. So that's what these cells are specialized to do. And the next slide kind of pictures these ideas. So if you look at the cross-sectional view, this is what biconcave means. Concave means curved in. So curved in there, but also curved in there, right? Biconcave. Well, you don't have to memorize these numbers. Like, it's a short distance no matter where you are for easy gas exchange. But remember this distance, the diameter, like 7.2 to 8.4 microns. The normal diameter. Because if you're smaller than that, it may indicate some anemia. And that size, allows you to navigate through single file through narrow capillaries. So they can stack. This shape allows them to stack. It's easier to stack flat pancakes than round beach balls, right? So that phenomenon is called like the rouleau stack. File through. Ability of RBCs to stack, file through capillary beds, capillaries. Period. Just go with that. And as you do, it's good to be single file because they all want to do the exchange, so it allows for better exchange if you're single file in a row as opposed to like side by side, I guess. Now think of the RBCs when you look at a blood smear. So the reason why they're a little bit translucent in the middle is because they're thinner in the middle. Okay. And also think about what they're carrying. They've ejected all the organelles, including the nucleus. They don't have a nucleus, but they have a lot of hemoglobin. Hemoglobin is a tetramer, so it's got 4 parts. Hemoglobin, a tetramer. And we'll go with 2 alpha chains, 2 beta chains. Notice that each piece of the tetramer basically has this iron-containing heme pigment, that big red disc. Each contains an iron-containing heme pigment. When you take biochemistry, you'll spend a whole test just on hemoglobin. So just know that. And know at the top there. Let's go through the numbers. One heme combined 102. Well, a hemoglobin has 4 hemes, so you combine 4 O2s for 1 molecule of hemoglobin. Now, 1 RBC is essentially a bag of hemoglobin. It's got maybe 280 million molecules of hemoglobin. So multiply it by 4, you can bind over 1 billion. 1 billion is kind of a difficult number to deal with if you do the units conversion. Avogadro's number and, all that. Just write this down. About 1.39 mils of O2 per gram of hemoglobin. That's the oxygen carrying capacity of hemoglobin. 1.39 mils O2 per gram of HB. Okay, so per gram. So how much grams are in our blood? Something like 12 to 18 grams per deciliter of blood in a normal person. 12 to 18 grams HB per deciliter of blood. A deciliter is 100 mils. Deciliter is more commonly used in other units than I've seen. So, all right, so that's the oxygen carrying capacity of hemoglobin. So let's say you want to estimate oxygen carrying capacity in a patient. Maybe you're a hematologist. Well, you simply do fractionate the blood, spin it down, and just kind of see how much you got. Call it a hematocrit determination. Let's go through all our terms. Hematocrit approximates the proportion of RBCs in your blood. Approximates proportion of RBCs in whole blood. Just spin it down and see. So, what matters is when you spin it down, the top portion is like that's the plasma. The dense portion that spins down is the RBCs, and that's your crit. So hematocrit, sometimes called crit, sometimes called HCT, all the same thing. It's the portion of red blood cells So you just go, we're going to do X, Y. So I went like this. This top mark doesn't matter. The proportions matter. So if you could kind of measure the proportions, normal HCT, let me give you a range, 37 to 54%. It's a unitless number because it's a proportion. Normal crit, 37 to 54. Okay. So if you're kind of below the normal range, maybe you're anemic. If you're above the normal range for whatever reason, that's called polycythemia. Another way you could estimate the oxygen carrying capacity of blood is to directly measure hemoglobin. So I'm just going to put my chemistry concentration brackets around hemoglobin, and I already gave you the normal range. 100 mils of 12 to 18 grams of hemoglobin per deciliter of blood, or that's 100 mils. And so I used to assign a physio-X activity. I no longer do that, but I put these here so we could talk through it. Let's say a healthy male, person with an average weighs slightly more. So if the normal range is 12 to 18, maybe the males are like, on average, 14 to 18. Maybe 12 to 16. Now, if you start to get into other situations, just regular healthy people, 1 and 2. Number 3, a female with anemia, for whatever reason. In this case, we say iron deficient. Maybe it's below the normal range, so give me a number, like 9, something like that. Okay. I'll just put a 9. You know what the units are. And then you can kind of like guess the others. If it's polycythemia and you have a normal range, well, something above 18. What do you think the effect of training is on blood for athletes? Think training increases your blood or decreases your blood? It increases. I mean, what is exercise? You're inducing hypoxia. And the body's like, okay, you're going to keep doing that. I'm going to make more blood. So if you kind of compare the two and look under the microscope.
Does that mean that people that live at higher altitudes have a higher.
That's right, and they do. And a lot of athletes, they live at high altitude for that reason. What you can't do is go to high altitude, train for a few weeks, then come back down and think you got it. You usually lose it by the time you drive down 2 hours from the mountain. You gotta live there to have the sustaining effect. A little bit higher hematocrit. So anyways, this is a sickle cell anemia. You see how the RBCs kind of pucker and sickle? And so that's kind of what those cells look like under the microscope. So obviously very low blood, very low hemoglobin containing RBCs for that type of anemia. There are different types of anemia, so let's go through them. Number one is simply you're losing blood for whatever reason. Slow bleeding ulcer or an acute stab wound. So anemia means low blood. So just blood loss is a cause, obviously. Nutritional. Maybe you need more iron because you have low iron or folic acid. The other ones include pernicious anemia, which is a lack of B12. So what I said earlier is B12 is found in meats, which is important for the absorption of iron, Fe, into the RBC. So you kind of need B12 to get to the iron. Well, turns out intrinsic factor from the gut mucosa is reduced in the elderly as the stomach mucosa atrophies. So intrinsic factor absorbs B12, but then you need B12 for the iron. So a lack of intrinsic factor could also be a cause. Lack of So if you have a lack of intrinsic factor in an elderly person, just give them a shot of B12. Or just take iron supplements. But it's all to kind of get the iron. For the iron-containing heme. Here's a iron-deficient anemia on the left, normal on the right. These are blood smear slides. Just take a drop of blood, put it on a slide, and just look under the microscope. And so notice for these blood smear slides, we don't see any plasma, just the formed elements. So you can see how the density is less. That's why the cells kind of clump together when the density lowers. But when it's a nice, comfortable density, you don't see that clumpiness. And also, if you take a closer look, there's a picture from a textbook. Not only do you have less density of cells, the cells themselves appear more translucent in the middle. So this is the iron-deficient anemia on the right. So in iron-deficient anemia, they call that hypochromic. RBCs appear hypo. It's a fancy way of saying they appear lighter. Chromic means color, so if they're more whitish because they got no color, what it means is low HB content. Not only do they have low HB, they're smaller if you were to measure them, which they don't do here, but the normal range is 7.2 to 8.4. But these cells are also called microcytes because they're less than 7 in diameter. So they're called, quote unquote, microcytes, less than 7 microns in diameter. There's another picture. This is from our collection. I just kind of took a picture and pointed to a few. Hypochromic, and they are smaller. There are genetic reasons as well. The sickle cell disease or thalassemia are the most common ones. Genetic causes of anemia. Thalassemia, there's a one bad gene. It's either the alpha or the beta chain. Okay, on one, because you inherited 2, right? So if you have one bad one, that's minor. Yeah, if you inherit 2 bad ones, that's major. So minor is the more common one. One bad alpha or beta gene. So you're going to have low blood because you only have one good gene of the alpha or the beta producing the hemoglobin. So the cells might be much smaller. The sickle cell anemia that causes a single mutation, a single amino acid mutation. That mutation, it makes the whole cell pucker or sickle. Causes RBC to pucker, sickle. Hence the name, sickle cell anemia. And that's what's shown here.
And the only way of treatment is through bone marrow?
Bone marrow, yeah, sure, transfusions. Blood transfusions can help. Bone marrow transplant would be a cure if you find a good match. So I'm pointing to a few sickle or puckled cells in some of our slides that we had. I also included a slide. I don't expect you to know the mutation, but I have a slide showing where it is. Okay, that location makes the cell pucker or sickle. Polycythemia, the other end of the spectrum, ignore the neutrophils, but look at the density of the RBCs. And I give you some numbers there. You don't have to know these numbers, but you do have this kind of secondary versus severe. The secondary is just due to altitude, living up in the mountains, Lake Tahoe or Denver. Because as you drive up the mountain, there's less atmosphere above you because you're getting higher and higher. So the air is getting thinner. The barometric pressure is dropping. So you inhale less O2 per breath. So the body has to adapt to that. So you get more blood. And that's called a climatization. Barometric pressure decreases with increasing altitude, resulting in less O2 per inhalation. So it creates, that hypoxic environment, not enough O2. For each 1,000 feet of elevation, your maximal oxygen consumption decreases about 3%. Good experiment is, let's say you're going to drive to Lake Tahoe or anywhere. Drive up in your jogging outfit. As soon as you get there, get out of the car and go on a run, and you'll see what they mean. It's like, oh my gosh, I haven't had time to acclimatize, and you just feel like you're out of breath even though you may be fit. I actually did that once. I was like, why am I out of breath? This really is a thing. But when you do acclimatize after a certain amount of exposure, 1 to 3 days, the changes are all to increase the oxygen carrying content of the blood so you prevent the hypoxia. So for example, decreased plasma volume, that's really a misnomer. What you're doing is you're increasing the proportion of crit. So therefore, by default, you're decreasing the proportion of plasma. Okay. So the effect is, remember the normal range? You can like double it. You increase pulmonary BP and vascularity, so you can pick up more O2 at the lungs. You're just perfusing the lungs with blood better. Increase skeletal muscle vascularity, so you can improve oxygen transport to the working muscles. Here's what I would take notes on. This is kind of how you increase the blood due to hypoxic environments. What you see there is altitude hypoxia. So the response is, after a few days, a day or 2 or 3, the kidney releases EPO. Okay, that's what it says for step 2. Think of it as a hormone. It's going to target the bone marrow. So they show proximal femur, EPO to bone marrow. Makes the whole chemocytoblast thing that we went through. Phase 1, phase 2, that whole thing. You just kind of increase the production of the RBCs. That's what it says for step 4. Increase RBC production. I'll put correct hypoxia. As the last step there. The thing about it is, let's say you have kidney failure or something, and for whatever reason, you don't have EPO. You do not correct hypoxia. With no EPO, you don't do that, you don't do that. So with no erythropoietin, for whatever reason, hypoxia not corrected. So there's synthetic EPO, so you can kind of get help.
Is that the whole dialysis part?
Dialysis?
Like,
Dialysis, usually we have kidney failure and you have to like filter out the blood to get rid of the toxins because the kidney can't.
and that's,
But yeah, I think if your kidneys are failing, you'd also need EPO.
okay.
Yeah. You can't produce it. Let's see, why would a kidney do it? What is kidney doing? It's monitoring your fluids. So yeah, it's filtering everything out. Well, there's something called blood doping, which is illegal, commonly done by athletes. Cyclists are the most notorious. Well, anyways, I thought I'd mention it. I've heard about it enough that you should be aware of what it is. Autologous blood doping is save your own blood, give it to yourself later before your athletic event, marathon, triathlon, Tour de France, whatever it is. But you do it by when you train. So while you're training, a few months before your event, take your blood out, store it in the freezer. Okay. The day before the event, thaw it out and reinfuse and give yourself a boost right before the event. I mean, it works, which is why athletes try to get away with it. If it's your own blood, I guess the only way you could catch it is you do random testing. I don't know, say test them here, and then test them right after the event. It's like, hey, wait a minute, there's no way you can get that boost. Even that's not really a smoking gun, but The idea is when you remove weeks before your training, the training will get your blood back to whatever your baseline is. And then right at your event, you give yourself a boost. So that's the thinking. I mean, this came out years ago, but the whole Lance Armstrong thing. I read that report and I was kind of alarmed. I mean, he knew what he was doing. He was trying to get away with it. I mean, he was really sly. I mean, he knew when they were going to be tested. He would mask. He would take all these diuretics. He would do everything. Okay, I don't want to get into it. I feel kind of bad throwing him under the bus, but he really wasn't a good guy in terms of that. He did a lot for testicular cancer awareness. There are very famous cases out there. I remember in the early 80s, 84 Olympics, the whole U.S. cycling team did the blood doping. And they didn't even use their own blood. They would use other people's blood. And they had all kinds of liver problems, and there's all kinds of cases of the blood doping, and how it's not good and how it's really not safe. The proper way that you would want to do it is if you're having surgery, and you know it, okay? And it's like, okay, let's save your own blood so you can use it for your own surgery. That's kind of when you want to store your blood. Athletes using it to get an edge is illegal in all cases. I think I want to stop here. I can cover blood typing and blood coagulation later. Okay, let's take a break now. Now when you come back from break, I'll just give you time to study the models.